In section 4.7, we are going to talk about optimization problems. Optimizing is when we either maximize or minimize something. So recall that the relative maxima or minima occur at x equals to c when f prime of c is equal to 0. So to find the relative max or the relative min, we need to find the first derivative and set it equal to 0. And when we solve, that'll give us either the relative maximum or the relative minimum, depending on the shape of the graph. Okay, let's just pretend that's the minimum. For quadratic functions, in order to minimize or maximize the function, we're going to set the first derivative equal to 0 and then simply solve. Now let's talk about marginal cost. Marginal cost is calculated as the total expenses required to manufacture one additional good. So often in business, we want to think about how do you maximize profit. And so in order to maximize profit, we have to find the profit function and we have to find the point that's going to maximize your profit and produce that many units. So in order to do that, we're first going to have to take a look at the average cost and think about how do we minimize the average cost. So the average cost is given by the total cost divided by the number of goods produced. Okay, so for example, let's say the cost of producing a particular item is 500,000. And for that, the number of items produced is 1,000 items. Then the average cost is going to be the total cost, which is 500,000, divided by the number of items produced. And so this will give us an average cost of $500 per unit. So the difference between total cost and average cost is total cost is C of X. That's the total cost of producing however many goods. But then the cost per unit is going to be the total cost divided by X. Also, I forgot to mention here that marginal cost could be found by taking the first derivative of the cost function, or C prime of X. So we're given a cost function, 36,100 plus 800x plus x squared, where x is the number of units. We want to find the cost at the production level of 1,400. So 1,400 represents the number of units produced. So we're going to replace the x with 1,400. We do a simple substitution, and the total cost is going to be 3,116,100 by plugging this into a calculator or desmos.com. Now the average cost is going to be the total cost divided by the number of units produced. So to produce 1,400 units, it costs $3,116,100. So the question is, how much does it take to produce one unit? So we take the total cost divided by 1,400, and because it's dollars and cents, we're going to round to two decimals. Per unit, it's $2,225.79. All right, now the marginal cost at the production level of 1,400. So notice here, the marginal cost is given by C prime of X. So for the marginal cost, we first have to find the first derivative. 36,100 is a constant, so that's going to just be 0. For 800x, it'll be 800, and for x squared, it'll be 2x. That'll be the formula for the marginal cost. And we want to find the marginal cost at 1,400, so we plug that in, and it's $3,600. So marginal cost, once again, it means the cost that it takes to produce one additional good. So if the marginal cost at 1,400 is $3,600, that means that it's going to cost $3,600 to produce the next unit, which is a 1,401st unit. That's the interpretation of marginal cost. Okay, now our objective to maximize profit is we want to minimize cost. So which production level is going to minimize the average cost? Well, so the formula for the average cost is given by C of X over X. So the cost function is 36,100 plus 800x plus x squared. So if we split all three of these terms of the numerator and divide them all by x, we get 36,100 over x plus 800x over x plus x squared over x. So to make these make these ready to differentiate, the x moves to the numerator and the exponent becomes a negative. So it's 36,100 x to the negative first plus 800, and then x squared over x is just going to be x. That is going to be the average cost. Now remember, to minimize or maximize any function, as we learned here, the maxima or the minima occur when the first derivative is equal to 0. So to minimize this function, we are going to take the first derivative, set it equal to 0, and solve for x. So the first derivative of the average cost, the -1 multiplies to the 36,100. We get negative 36,100. Then we subtract 1 from the numerator. That gives you a -2 for the exponent. 800 is a constant, goes away. X, the derivative of that is going to be 1. So that is going to be the first derivative of the average cost. Then we are going to set that equal to 0. Remember that we can't have any negative exponents in our final answer, so we move it to the denominator and make it positive. So we get negative 36,100 over x squared equals to 1, or plus 1 equals to 0. Let me repeat that. Negative 36,100 over x squared plus 1 equal to 0. We set it equal to 0 because in order to minimize cost, we set the first derivative equal to 0. And then we use some algebra to solve this. First thing we do is we're going to move this entire term to the other side by adding it. And then we want the x squared to be on the numerator, so we're going to multiply both sides by x squared. And then finally, we square root, and we get 190 units. So when we produce 190 units, the average cost will be minimized. And then the minimal average cost, we're going to just, so we know that 190 units minimize the average cost. The average cost function is up here, the 36,100 plus 800x plus x squared over x. We now know that x is 190. So we're just going to replace all the x's with 190, and we get our minimum average cost to be $1,180. Here's the next problem. There's a box, and the box has a square base. So if it's a square base, then the length and the width of the base are going to be the same. Now, we want to have a volume of 97,556 cubic centimeters. And we want to find out the dimensions of the box that gets us this volume, but by using the least amount of material. So our objective here is we're going to minimize the amount of material used while still building a box with this volume. Okay, so first, let's find a surface area of this box. So surface area is going to be the area of all of its surfaces added up. So let's break the box down by its different surfaces. So first we have the base, which is going to be a square, and that base is going to be x times x. And then we have the area of the sides. So we have 1, 2, 3, 4 sides, and then we have the base. So the area of the base is going to be given by x times x, which is x squared. And then the area of each of these sides is going to be given by length times width, which is going to be x times h. And then there's 4 of them. So the area of the total area of the 4 sides is going to be 4xh, which is 4 times xh. So the total area of this box is going to be given by the area of the base, which is x squared plus 4xh. Okay? All right, so what do we do with this? So now that we have the area in terms of x and h, we don't want that. Why don't we want that? Because we're looking for the length of the side that's going to maximize the area. So, that's going to get us the volume with the minimum amount of material used. Okay, I'm sorry, we want to use the minimum amount of material used. So in order for us to do that, we want to have everything in terms of just x. So here's the next thing that we know. We know that the volume, which is what we're trying to get as 97,556, is given by the length times width times height. So the length is x, the width is x, and the height is going to be h, which is going to be x squared times h. That is a formula for the volume. And we know the volume is equal to 97,556. That's the volume we want to build. So from there, as you can probably see where we're going with this, we want this to be We want to write everything only in terms of x. We don't want the h in there. We want only in terms of x. So in order to get this in terms of x, we're going to solve for h, which is going to be 97,556 over x squared. And by doing that, we can now replace the h with this term and get everything in terms of x. Okay, so now our surface area is going to be x squared plus 4xh, but we want everything in terms of x. So instead of h, we're going to replace that with 97,556 over x squared. If you simplify a little bit, we have the x squared, can't do much with that. 4 times 97,556, that's going to be 390,224. And then x over x squared, we're going to have an x on the denominator because one of the x's on the numerator cancels out with one of them on the denominator, so we have just an x left on the denominator. That's going to give us the area. So that's just going to be part A. All we did was we found the area. And now in part B, we need to find the first derivative. Okay, so to find the first derivative, we have our area, which is x squared plus 390,224 over x. But in order to make this ready to differentiate, the x has to go to the numerator. So we're going to rewrite this as x squared plus 390,224 x to the negative first. And then we're going to use our rules of differentiation. So the 2 comes down and becomes a 2x. The negative 1 multiplies to the 390,224, so we get negative 390,224, and we subtract 1. That gives you x to the negative second. We can't have negative exponents in the final answer, so this becomes 2x minus 390,224 all over x squared. So that's the first derivative. The critical value is, well, there's 2 ways to get a critical value. One, by setting this equal to 0. The other, setting this undefined. Now, undefined is going to be where x is 0, and we can't build this box if x has a length of 0, right? So for our critical value, we're not going to worry about when this is undefined, but we're going to worry about when this is equal to 0. So we found the first derivative, and to find the critical value, we set the first derivative equal to 0. So let's do some algebra. I'm first going to move the negative 390,224 over x squared to the right by adding it, and then I multiply both sides by x squared. So I get 2x cubed equals to 390,224. I divide by 2, and I get x cubed equals to 195,112. In order to solve for x, we need to raise both sides to the power of 1/3, which is the same thing as cube rooting, and we're going to get x equals to 58. So the critical value is going to be 58. Next, we want to determine if this critical value is a local max or local min. So to do that, remember local max, local min, we're going to use the first derivative test. So we choose a test point to the left of 58 and a test point to the right of 58. And what we get is that the sign of the first derivative is negative in the first interval and positive in the first interval. So what does that tell us? Well, it tells us that if this is 58, then the function is going to decrease, hit 58, and then it's going to increase. And that means that 58 is going to be a local minimum because it's going to go from decreasing to increasing, which makes it a local minimum. Okay, so because it is a local minimum, that means we are going to use x equals 58 in order to minimize the material while at the same time maximizing the volume and getting the volume that we want. So the length of each side would be 58, and the height, we can use this formula right here. We can use the formula h equals to 997,556 over x squared in order to find the height. But I think we're just looking for the x value in this case, which is 58. All right, lastly, a farmer finds that if she plants 50 acres per tree, each tree will yield 75 bushels of fruit. So this problem we're going to actually do in class. So what I'm going to do is I'm going to have you guys copy this down, and then we'll talk about it during class. So copy down this information and we'll go over the problem during class.